So in this section, we're going to talk about exponential functions. I usually like to start out with, there's an old Chinese legend about, the emperor was out, anciently, and a cart was going to hit him, and this peasant saves his life. And so the emperor says, I'll give you, whatever you want, half my kingdom. And the peasant says, well, take a checkerboard and put 1 grain of rice. So a checkerboard is 8 by 8. Let's see, 1, 2, 3, 4, 5, 6, 7. All right, we'll divide that one. Anyway, pretend like this is a checkerboard. And he says, put 1 grain of rice on the first square and then double it for the next square, and then keep doubling it until we're to the last square. And so, the legend is the emperor runs out of, money because he gets the peasant gets all the rice and all the wealth. So that's an example of what we call exponential growth. You can also have exponential decay. So let me give you some examples of exponential growth. Population growths are usually exponential. We're going to talk a little bit about compound interest. That's based on the principle of exponential growth. You're putting some money in and it's going to accrue interest over time. It's going to keep growing. Inflation, unfortunately, that's often exponential. Let's see, we talk about things like bacteria and diseases. If you look at the graphs of how COVID-19 cases have grown, you'll see an exponential model there. And exponential decay, things like radioactive material and half-lives. It can also work for population growth, decreases, I guess. Population, some countries, their population isn't growing, but rather it's decreasing. Those are the ones I can think of right off. As opposed to a linear growth. Now, linear growth, we've had that before. So let's say we have some function f of x equals 2 times x. And say you're going to work for a company and they're going to pay you $2 for every day that you work. So the first day you work, you get $2. Second day, you get another $2, so now you have 4. The third day, you get another $2, and now you have 6. And you're doing this based on, a table of values, x and f of x. And then 4 days, you'd have $8. 5 days, you'd have $10. And on 6 days, you'd have $12. But what happens if we look at an exponential growth? Well, let's say you're going to have f of x equals 2 to the x. Now, we're going to have to say, if a boss comes and proposes this for you, what they're going to say is, I'm going to give you, just not even working for a day, I'm going to give you $1. So they got to start you out with something. And then the next day, I'm going to double it. And then on the second day, I'm going to double what I gave you the day before. And then on the third day, I'm going to be doubling what I gave you the day before. This is back to the checkerboard model here. On the fourth day, now you're getting $16 on that day. On the fifth day, $32. And then on the sixth day, $64. Now, if you added, obviously on day 6, you're getting $64. This was on day 6. That's a total of $12. You're getting 64 plus what you made on the other days. So that's an example of exponential growth. They go up very quickly. The model for an exponential growth is a basic model. It's a function where you have some base to an exponent that's a variable. So that's what's important to note, is that the variable is in the exponent. Now, just like our other functions, we can do transformations. We can have a number, a multiplier in front. And then we can also do things in the exponent. But right now, we're just going to kind of keep it this way. There are a couple things we have to keep in mind. One, b has to be positive. The base has to be greater than 0. And b cannot equal 1. Because if you just keep raising 1 to an exponent, it's just still going to be 1. Okay? So those are some things to keep in mind. An exponential graph where A is, well, let's go to a basic one. Let's say we have a function f of x equals b to the x, and let's say that b is greater than 1. It's going to go like this. And it changes its shape based on what b is, so it does matter what b is, but that's going to be the basic shape. It's going to rise very quickly. It's going to have an asymptote at the x-axis right there, and you'll see it's increasing at a quick rate. Okay, so one of the things they want us, that's a little introduction to exponential functions. One of the things they want us to do is be able to recognize an exponential function. And it's going to come back to this idea that it looks something like this. So they give us some functions here, and we're supposed to say if it's exponential or not. Now, if you look at this one, you have a base of 4, and then what's the exponent? Well, it's all this up here, but notice that the variable x is in the exponent. You have to be really careful when you write these. You want to make sure the 4 is the base. You could multiply this out to be 3x minus 6, but you have to make sure all of that's in the exponent if that's what you mean, you know. You could write it that way. But yes, this is an exponential. So it says, which of the following are not exponential functions? So this one is exponential. It is an exponential. This one, it looks similar. It's got an exponent, but where is the variable? It's in the base, not the exponent. So this is not exponential. In fact, that's a polynomial function that we talked about in chapter 5. Now, what about this? This looks different. Well, it has a base. The base is not 1, and the base is not negative, so it clears that part. The variable is in the exponent, so yes, this is exponential. And the last one, j of x, you have a variable in the exponent, but there's a problem with the base. It's negative. And so in this case, you have b being less than 0, and so this is not exponential, okay? You run into a problem with a negative base because it's going to go, as you change the exponent to an odd or an even number, it's going to go positive, negative, and you won't get that curve like an exponential function has. So, okay, that's an introduction.